Right, we're on to day 12. And it's about to open in 1 minute. That was a loud motorbike. So, yep, just gotta wait for this to open. Oh, we have someone on my leaderboard now. Who's Pararonia? Who's that? Were they in chat the other day? Alright, I gotta stay on this page. Okay. I mean, I'm not gonna rush this. Because I'm lazy. There we go. 12. Hill climbing algorithm. Yay. You try contacting the elves using your handheld device, but the river you're following must be too low to get a decent signal. Okay. You ask the device for a height map of the surrounding area. The height map shows the local area from above broken into a grid. The elevation of each square of the grid is given by a single lowercase letter, where A is the lowest, B is the next lowest, and so up. So Z, okay. Got S for our current position. E for the best signal. Your current position is elevation A, and Z would have the so Z is the highest, okay, yeah. So you want to go to the highest point. You'd like to reach E, but to save energy, you should do it in as few steps as possible. Alright, I need to look at this input to get a better sense of what... So it's a 2D grid. And these are like pits. And this is like a mountain over here. Okay, cool. One square up, down, left, or right. Okay. The elevation of the destination square can be at most one higher. But you can actually drop down much lower. Okay. Start in the top left corner. Your goal is near the middle. You can start by moving down or right. But eventually you'll need to head toward the E at the bottom. From there you can spiral around to the goal. Uh-huh. Yeah. 31 steps, the fewest possible. What is the fewest steps required to move from your current position to the location that should get a signal? So this is just Dijkstra's. There's no real trick to this. Just interpret the graph and implement Dijkstra, right? Okay. Hang on. Alright then. Let's code Dijkstra. Do I remember Dijkstra? So we need... Hang on, I didn't save the input. There we go. Okay, so we need to just pull out the map. So we need a let's say grid equals just empty list. Or line in f.read lines. Grid.append line.strip. So that would just give us the map. So the start, I'm gonna remind myself what is the hello DJ, what is this stream res? 1080p. Yeah, that should be it. 1080p and 48 frames per second. So S is the start. Do I even see S here? Didn't even know that was an option. I think... Oh, there's lots of options. I mean, I go with 48 for like coding streams because you don't even need as much as 60 for those. Well, I can't see the values now, but yeah, there's a drop down in OBS. I think there's several different values you can choose. You just can't go above 60. I guess we need to just find the start and the end. So 4 row in grid. Well, we need coordinates. So for I in range, figured it would just be 3060. But then you have, yeah, we have lots of legacy frame rates that used to be used, like 29.97, which is actually still used in America for TV. So I guess they would support those as well. And 25. Which is used in TV in Japan and Europe. I am range. Hello, Mormon. My coding. The goal is advent of code. Let me see. The US mostly uses 60 now. Oh yeah, digital TV, yeah. I guess for like movies, but movies are still 29.97, aren't they? But yeah, TV is I guess 60. Yeah, so Mormon, the puzzle here is, well, this is a long-winded explanation. Basically, this is a map. A is kind of the lowest elevation. Z is the highest elevation. And you have to find your way to the highest point, which is here. E. Wait, is that even appearing on stream? Just about. Starting from A. Starting from... Are we playing Dwarf Fortress? This should be, yeah. Maybe they took inspiration from Dwarf Fortress, because you do have elves in Dwarf Fortress. Where am I starting anyway? I can't see where I'm starting, but there should be an S somewhere. But it's basically Dijkstra. You're allowed to go one step up elevation, or you can drop down any number of steps. You can drop down any height value, but you can only go up by one height level. So you got to find your way to E. So yeah, it's basically just Dijkstra, or A star even, but I mean, for the purpose of this, you can just use Dijkstra. Yeah, so let me switch back. So I gotta remember how to code Dijkstra. So for I am range, wait, so we need to find the height here. So height equals height, width equals length of grid, length of grid, first element. You have to write code that converts letters into lines to make topo map. Not... You could do that, and then you'd end up with a graph, and then you just use a normal graph algorithm. But I would just basically kind of integrate that into the neighbor function, so I always know which coordinates I can get to from any given place. So the key really is just writing the neighbor function. So I wouldn't bother making a graph, what's topo short for? Topological map or topographical map? Then overlay that on Google Maps to find the location. You just, for this coding challenge, you just have to output the shortest distance and paste it into the browser. And we'll see if I got it right then, just for this given input. There's a different challenge released every day. It's a good site. I recommend it. Yesterday's was quite good, actually. It was involved a bit of number theory. Very small amount of number theory. Let's see, so we've got the height, we've got the width. So I need to find the start. So for I in range... And there'll be a part 2, so when I solve part 1, they'll reveal part 2, which will be some twist or something on what I've done so far. Yesterday, the part 2 was a pretty significant twist. Like, it very much changed how you had to calculate things. Sometimes it's not much of a twist. It's just like, just do this, just add this line or something. All right, so I didn't end up catching it. Who won? I believe I didn't watch it either, but the match, the As Dreams match, I believe Shawnee won. Shawnee got to 99. But Wugger will be in the loser bracket now, so he'll get another chance. He'll be facing Chai. Yeah. Flying range height. Wugger, why you throw? I mean, he was probably on his way to 99 as well. At this point, it's just who gets to 99 first, which is crazy. How's the World Cup been treating you? I have not been following the World Cup at all. I mean, I never really watched the World Cup, but this year in particular, I'm Grid. Hello, C6. Is that a 1? C61F. Grid can be shortened to grid. Yeah, you could do it that way. I guess the reason I did it like this is because I'm every single challenge I'm always doing 4-line and f.read lines, so I have custom logic. But yeah, I won't bother changing it now. It's a thing where millionaires play in stadiums built by slaves. Yes, exactly. Yeah, no, Qatar is a bit of a shitty place to have a World Cup. Well, just a shitty place in general, if I'm being honest. Hang on, what am I trying to do here? For I in range, yeah, for J in range width. If grid ij equals s, was it s? That's the starting point. Yeah. Okay. Start equals ij. And if it's, I believe we're trying to get to E. And a goal Alright, that just extracts the start and goal. Now we need to implement Dijkstra. So we need a queue, right? A priority queue. Alright, DIJ, I'll try. I'll try and not finish this. I don't think I will. I need to. It takes me a while to write Dijkstra from memory. I haven't done it in a while. From queue import priority queue. So we need queue equals a new priority queue. Queue dot put. So we need to put the start node into the priority queue, so that's where we're starting. We need, what else do we need? We need a closed set equals a set. We need what's it complaining about? Start can be undefined. Well, it won't be. While q dot, well, not q dot empty. Current equals current. Dist equals q dot get. So this extracts the next node to visit and the distance. Do we need the distance? Yeah, we do need the distance. Oh, so we also need a dist map, which records the shortest distance. So dist map start equals 0. All right. This dictionary creation could be written as a dictionary literal. Oh yeah, of course. Okay. Self unfulfilled. What? While not q dot this method is likely to be removed at some point. Use queue size equals 0. Apparently we're supposed to be encouraged to use queue size equals 0 now. Okay. Well, I'll do that. While not q dot, what is it? Queue size. So while q.q size, basically. While q.q size. Is that what they want me to do? Why is it complaining about self unfulfilled? What? Okay. Oh, because that's why I didn't put brackets. Okay. Okay, so if now we need to do a goal check. So if current is goal, print dist. No, yeah, print dist I've got this the wrong way around. Dist current. Dist is the first parameter. And break out of this loop. So that means if we're expanding the goal node, that means we found the shortest path. Right? So what else? I think we want to also check if it's in the closed set. If it's in the closed set, that means we've expanded it before. So we shouldn't expand it again. That means it's like just lazy deletion. We are dealing with a longer path to this node. We don't want to, so continue. Okay, so at this point, we add it to the closed set. That means we've confirmed this is the shortest path to current, and we don't want to expand it again because there'll probably be other paths in the priority queue that we added previously. Okay. Oh, so for Dijkstra you need a G distance or something. G dist. So this is the distance Wait, no, that is dist map, isn't it? Dist map is the distance from the start all the way up to this point. We'll call it G distance then. Because you've got a G distance and you've got a F distance, but that we're not doing A star, so. Alright, so now we need to look at the neighbors. And at this point, this is where okay, we're gonna have to write a custom neighbor function. So define neighbors of okay, so of just neighbors of one cell. Let's say xy equals or ij equals cell. Just extract the I and the j. And let me look at the thing again. So we're allowed to go up, down, left, or right. Yeah. Okay, so for delta x, well, let's say delta I, delta j in, and then we have a list of we can either do -1, 0, +1, 0, zero. Let me just turn my air conditioning on. Did I leave the remote? Not within reach, apparently. I mean, this problem if I already had pre-prepared a Dijkstra script, which is a totally reasonable thing to do, then this will be super fast to solve. Okay. So we've got new, oh no, let's say neighbor equals so the new coordinates are I plus di j plus dj. Okay. Now we need to do a out of bounds check. So if not 0 is less than or equal to neighbor I just less than height. Oops. Continue. Just do the same for J. So we skip it if it's out of bounds. Otherwise, it's a valid labor if the height is not more than one step above our current height. So if, how do we do this? Grid. Alright, so when we find the start and the exit, I think we should replace the S and the E with A's and Z's, because otherwise they don't fit within the height map correctly. So that's a bit weird. So start equals ij grid ij equals A, so that it's correctly has the correct height. Grid ij equals, and Z, they said Z was the goal is guaranteed to be on level Z. Alright, so now if grid neighbor I neighbor J is strictly greater than grid I j plus 1, continue. Anything else is fine. Could drop down. If we've got this far, then we put it into the neighbor map. So neighbors.append neighbor. And then finally we return the set of neighbors. Alright, so this comes before this. So let's just say Dijkstra. I think it was only until Witcher 3 that I learned how to pronounce Dijkstra. I always called it Dijkstra, and I'm pretty sure different professors of mine would have different pronunciations for it, so but in Witcher 3 there's a character called Dijkstra. Alright, so where was I? Now we need to extract the neighbors. So for neighbor in let's just call this get neighbors, just to be a bit clearer. Get neighbors. So we are getting all valid neighbors that we are allowed to reach. They're one step away. Damn it. We don't need Dijkstra for this, do we? One step away being the operative phrase here. This is just breadth first search. So actually, so I can simplify this. I can just say, we might need it for part 2, but then again, probably not. Or it could be that distance, different, going up several steps costs more steps. Maybe that will be the part 2, I don't know. Alright, so for now, let's just say Q equals... So not priority queue, it's just an empty list. With start in it. So we don't need to do that. I'll keep it in case this comes up. So I can still say gdist. We do need closed set. So, okay, let's comment this out. While q current equals... But we don't actually want a list. We want an actual queue. Breadth first search. Yeah. This would be depth first, the way I'm doing it. We want breadth first to make sure we get the shortest distance. Alright, so we need a q dot q. We need this, so we put the start in there. So there's no risk of things being put in multiple times, because the moment you extract it, you found the shortest path to that. So q.put start, gdist start 0, close set equals set, while q current equals q.get. So basically this logic again, if current is goal, print dist of current break. We don't need to check if it's in the closed set because things will only come out once. So for neighbor in, so it's pretty much the same but without the priority queue implementation. So for each neighbor, if neighbor in closed set continue, so we don't go back in a loop. Oh, and yeah, we do need to add it to the closed set. Actually, the moment we put it in to the queue, that's when we add it to the closed set. Hello, DJ. Coding is coming along. I've simplified this because I was going to use Dijkstra, which is a more complex algorithm, but then I realized in a grid map, every distance is 1 between your neighbors, in which case you can just use breadth first search, not Dijkstra, which is a simpler algorithm. So I'm now commented out some stuff that I was doing before and now just rewriting this using BFS. So g dist of the new neighbor equals g dist of the current plus 1. Q dot put the new neighbor into the put the new neighbor into the queue, and we say now we add it to the closed set, so we never deal with that neighbor again, because that's guaranteed to be the shortest path because of the order in which we expand nodes. That's the point of breadth first search. Wait, what? Closed set dot add. What else? Is that it? Is that breadth first? Breadth first search? Am I using the gdist? Yes. Am I using the closed set? Yeah. Should just try running it then? 12. Oh, because it's a... Also, I just realized you can't +1. These are strings, the characters. Should we just convert them to their ASCII value or something? Hang on. So... you might as well. Convert A to 1, Z to 26 or whatever. So if I want to do that, no, we can keep the letters. Just do the check in our get neighbors. So let's say we'll just put it as a list. That everything should still work now, but it's going to be a list, not a string. That means it's actually what's the word? Mutable. Yeah, mutable. So this check here, so we want, what is it? Ord. So that just gets the ASCII value of it. Grid, neighbor I, neighbor J. Wait, what's going on here? Neighbors dot append. Ord needs a string, but it got a list. Wait, what did I do here? Grid dot append list of line dot strips. That should turn. No, that should be fine. Alright, let's try printing the grid, see what we've got here. Well, let's correct these compilation errors. Neighbors.append. Neighbor. 497. That works then, but it doesn't like this, but... Alright, 497. Could that be the answer? I don't know. Let's try it. As I say, for every one of these challenges, I don't feel confident, because I'm always just running it out of the box, just after I've done lots of stuff without testing. So it's how many steps to get down? No, it's how many steps to get up. You want to climb to the highest peak So you're allowed to go one space up, or you can drop down many spaces. You're allowed to go one height level up, or you can drop down many height levels. But this is a bird's eye view, so you can up, down, left, right means like north, south, east, west. Where is Z? Oh yeah, we're trying to get here, basically. Oh, here's S. We're starting here. So just looking at that map, I imagine you'd kind of want to... Well, you can go on C's, but if you drop down to A, you can't get back to C. So I guess you want to skirt around this mountain. Yeah, skirt around these ravines, essentially. And then when you get to here, you probably want to... I don't know. It's probably some spirally path to get up safely. Alright, what was it? 497. Let's try that then. Whoops. It's correct. I mean, it's breadth first search kind of just works. It's hard to get wrong, really, because it's always the same. The key, really, is getting the neighbor function correct and the interpretation of the map. That's where you can go wrong more easily. Alright, part 2. As you walk up the hill, you suspect that the elves will want to turn this into a hiking trail. The beginning isn't very scenic, though. Perhaps you can find a better starting point. To maximize exercise while hiking, the trail should start as low as possible, elevation A. The goal is still the square marked E. However, the trail should still be direct, taking the fewest steps to reach its goal. So you'll need to find the shortest path from any square at elevation A to the square marked E. So we're trying to... Okay. This is not too difficult, but you just have to try multiple starting points and see which gets to the goal quickest. So okay, let's look at the example, just make sure I've understood that. 6 choices for the starting position, yes. Including the S. Yeah, okay. So first we need to extract... Okay, so if grid IJ is AS... Okay, let's say in SA. So we want to have a list of starting points that we're going to try. So if it's either S or A, then starts dot append that and rewrite it as A, that's fine. There's one goal, rewrite it to Z. Get neighbors is still the same as before. We don't need any of this. So basically we want to wrap this up as a method. Well, we don't have to, we could do it in a for loop, but it's kind of nicer to wrap it up as a method. So define, let's say BFS for given start. So all this remain the same, put start. So here we want to return the shortest distance found. And that's it for writing the method. Put the start in. We don't change, we don't mutate the graph in any way. So it's just a case of print min of starts. Wait, how do you use the min function again? We want lambda Wait, I want to use the min, but that's just going to give me the argument, isn't it? It's going to give me the start, but not the... Oh, whatever, we can do it this way. Okay. Best equals min starts lambda... No. Key equals lambda. Key equals BFS. Can you just do that? And then print. We'll just have to call BFS a second time. I don't know if there's a way to avoid doing that. There's a lot of A's. But it shouldn't take that long. It is taking a long time. Should it? Okay, I'm doing this the wrong way around, aren't I? This is the trick. You're not supposed to start from all the starts. That'll take a long time. You're supposed to start from the goal and find your way to an A. That's what they're expecting you to do. I still wouldn't really have expected it to take this long, but then it is fairly big, I suppose. I suppose so. Yeah, so you start from the goal. It's a lot of A's, but then it's... How many are we talking? It's like... If it's, say, half this map, 40 times... 200. Yeah, okay. That's that. Therein lies the trick. So we actually want to start from the goal, because then the moment we find an A, we stop. That's the closest A. We don't need to check any other A's. Right. So what do we change? All right, let's stop this. So everything's the same. Got A's. We don't need starts. That's not a thing. We don't need to record the start. If it's E, goal is IJZ, that's fine. Get neighbors. We kind of want to invert this, don't we? So we actually want to go down backwards. So we want to say we don't want to drop by more than one, because we're doing a backwards path here. So if if it's less than -1, that's too big a drop. And now BFS. Given a start, that's fine. We can keep this method the same. The only thing we need to change is if current, if instead of is goal, we want to say if grid current 0, current 1 is an A. Then we return the distance. Don't do that. We start from the goal. Alright, will that work? 492. So 497 we had before. It's now found something with 492, which is slightly better. I was hoping for something a bit... Does that actually make sense? Let's look at the map. Because we started from all the way over here. We had a path of 497. So we're saying... that does actually make sense, because most of these A's are actually inaccessible. They're surrounded by C's, so you can't get out of them. The only A's next to B's are actually kind of all the way over here. So it does make sense that it wouldn't be much far off. Oh, it's actually this first column. It's only this first column. So we found the distance from here. So the shorter distance would be just be somewhere like one of these A's maybe. Or anyway, I don't need to try to interpret the answer. Let's just try it. Woo! So yeah, it's BFS. Great algorithm. You can do it using a queue. You could do it using a Python list as well, but that would be inefficient. I mean, I could try it just to see how. It would still work, but it's just not good for large maps because you can't. It takes linear time to rebuild the map every time you take an item out. So you should use a Python queue for it. And there's no reason to use Dijkstra here, because all edges are of distance 1. If you had a more complex map where there were different edges have different distances, you could use Dijkstra. And if you wanted to improve on that further, you could use A star, which is what I was initially writing, which is kind of better performance than Dijkstra, but it uses a heuristic, which for these kinds of maps is usually easy to find a heuristic. You just use like the Euclidean distance or the Manhattan distance or something. And if you're writing AI for video games, this is the sort of stuff you're doing most of the time. Pathfinding. It's like, it's all about finding how to get your character from A to B. Or the enemies, getting the enemies from A to B. I guess that's why devs like making zombie games, because zombie games, you don't really have to give them smart AI, smart pathfinding, because it's kind of expected that they're kind of dumb and can't find their way around. So you can get away with it. Players won't complain, because it's like, oh, this zombie couldn't figure out how to climb these stairs. Well, it's a zombie, it's not supposed to. But, for non-zombie games, it's expected that they know they can figure out how to go around obstacles, climb stairs, stuff like that. Use shortcuts. Like hill climbing is... So this is not actually hill climbing algorithm. Hill climbing algorithm is where you always pick like the path of steepest ascent or something. Or you just keep going up. But this will get you stuck at a local maxima sometimes. Hill climbing algorithm is an algorithm for finding the peak, local maximum. So in this map, you could argue that it's hill climbing because you're kind of... All of these are troughs, they're not peaks, so they're all like lakes. But if you were to... but hill climbing wouldn't tell you how to get from all the way over here to this mountain in anyway. Because there's no path of greatest ascent here, so you would just go around in a arbitrary walk and you just get lost. Yeah, also in hill climbing you can go up any height. Ideally you want to go up the highest height you can per move. Alright, yeah, that was a good problem. This is one where you actually need textbook knowledge of an algorithm. I mean, you could write BFS from first principles without knowing BFS, just using common sense. But who would do that? Like, if you are competent enough to do that, you've probably already seen BFS anyway, so you probably know the framework for BFS. Which differs from DFS. DFS is the more intuitive one, because that's the one you would actually solve. That's the one you would actually use if you were in a real maze. In real life, physically in a maze, where you can't keep a queue data structure because you're a guy in a maze, then you would use DFS, because then you just keep going as deep as you can, then turn back and go as deep as you can the next way, and so on. You only need to keep a pointer to where you came from before, which is easy enough for a human to do. Isn't maze just stay on the left right hand side? Sort of. So there's a game that was released recently, which was a parody of The Witness, which is called The Looker. And they actually trolled players who used the left-right hand algorithm because it doesn't work on that particular maze, because they've specially designed it in such a way that it doesn't work, which is really cool, because myself included and all players who played that just went for the left-hand algorithm or something, and then they end up back at the start and they're like, what happened? It works as long as... I mean, mathematically speaking, the left-hand, right-hand algorithm works as long as the map is the grid. Let's look this up. Something about it being simply connected. I think the path from the entrance to the exit essentially has to split the map up into two. But in the Looker, you're not actually getting to an exit, you're trying to get to the center of the map. So there's no guarantee that the left-hand algorithm will bring you there. If the maze is simply connected, that is, all its walls are connected together or to the maze's outer boundary. Yeah, so the walls have to be connected to the place you're trying to go. But if you had like an inner wall, which was disjoint from the other walls in the middle of the maze, that would not be simply connected. So the only way you could get to that is, well, you can't get to it using the wall following algorithm, because you'd actually have to take your hand off the wall and put your hand on the new wall. So this algorithm won't work. You can clearly see that it won't work, because your hand would never actually touch the inner wall. So that was really cool. The Looker is a great game, by the way. Even if you haven't played The Witness, but it is a pretty funny parody of The Witness. It's free as well, and it's short. It's like 2 hours or something. But yeah, I watched streamers play that, and they would use the left-hand algorithm. They would get to the exit, and they would be like, wait, I thought left algorithm always works. And then they would do it again, because they thought they'd done it wrong. And then they'd do it again from the exit. Like, what's left-hand algorithm? I believed in you. So, and incidentally, the left-hand algorithm is the algorithm the monsters follow in Azure Dreams. Specifically the left hand. They always follow the left wall and turn left at every junction. And that's what the speedrunners, or at least the good speedrunners, use when they're deciding which way to go. Or abuse when we're hanging around in junctions and we see lots of monsters coming, then we kind of go down one path a bit, wait for them to turn left, go here to wait for these guys to turn left, and so on, just to keep our paths clear. But yeah, I wouldn't expect Advent of Code to go as far as A-star algorithms. BFS makes sense. DFS makes sense too. Although there's no real situation where you'd ever need to use DFS, because DFS doesn't have any... DFX is just easy to code. BFS has one great result, that it's optimal. DFS just arbitrarily gets you somewhere, so there's no problem you'd ever need DFS for. Alright. I need to go out and get lunch. I actually did this one on time, so let's see how I compared with the rest of the world. How do I actually do that? No, that's... Here we go. Day 12. Rank 2898. It's not my best rank. 2222 was my best rank so far. That was the one I solved in 14 minutes because that was pretty easy. This one took me over 24 hours. Well, there really are a lot of people doing Advent of Code. I didn't realize that. Wait, how many people? How do we see how many people there are doing it? I don't know. A lot, apparently. Well, over 200,000 people have solved problem 1, so that's a good indicator, because anyone else probably got bored of it and didn't continue. Alright. So yeah, I'll be back tomorrow. Maybe around the same time, which would actually be on time the moment the problem releases. We'll see. Alright, see you later, DJ. And Mormon and C6 as well.